Hello students, welcome back to Math 332 Linear Algebra. In this video, we are going to look at some of the applications of diagonalizations. In particular, we are going to see how we can use the process of diagonalizations to solve a system of differential equations. And also, we're going to see how we're going to use diagonalizations to solve what we call a difference equations. All right, so without further ado, let's get right to it. Let's first look at the objective for this section. So at the end of this video, you should know how to use the diagonalization process to solve a system of differential equations, and also need to know how to use the diagonalization process to solve a difference equations. So what is a system of differential equations? Okay, for that, let's look at this particular example here. So you have two tank 1 and tank 2. So inside the tank, it contains salt water. And you can see that you have like pure water going into the systems at the rate of 5 liters per minute, and then you mix with the salt that is in tank 1, and then you can see that the salt water will leave tank 1 and go into tank 2 at this particular rate, 9 liters per minute. And also there's a thorough mixing in the second tank, and the second tank here also have some of the salt water moving into tank 1 at this rate of 4 liters per minute, and you also have some drainage coming out from the second tank at 5 liters per minute. So the things that we are interested in is this quantity, x1t and x2t. They stand for the amount of the salt at tank 1 at time t, and the amount of the salt at tank 2 at time t. So we would want to know this quantity, but this quantity is difficult to obtain directly from the gauges. So we can't really have a gauge that measure of this thing. We can have a gauge here to measure the 5 liters per minute of pure water coming into the first tank. We can also have a gauge here to measure the rate of the salt water leaving the system. We can also have a gauge here. We can also have a gauge here. So we can measure the rate pretty easily, but not this quantity. But this is a quantity. These are the quantity that we are interested in. So when we try to construct equations for this particular system, because of the rate or the rates that is involved, it is no surprise that the equations that we can easily set up is going to be equations involving rate. So these are differential equations. Differential equations is nothing but equations involving derivative. And you know from calculus, derivative has something to do with rate. So this is basically a rate equations. And so unfortunately, the dx1 dt, okay, is measured as the input rate of salt minus the output rate of salt. If you set up the equations, it's actually not only involving the quantity x1. So the x1 dt is not only involving the quantity x1, it also involves the quantity x2, because if you look at the picture here, clearly all the x1 and x2 are interrelated. Okay, so they are not separate system. They are one system. We have a lot of interrelationship among them. And if you try to write down the equations for the rate, okay, dx2 dt, you can also see that this dx2 dt is not only involving x2, it also involving x1. So in order to better describe this entire situation here, we will have to set up what we call this system of differential equations. And you can see here x1 here, you have x1, but you also have x2, and this x2 is governed by these differential equations, and this differential equation is not only involving x2, it also involves x1, so they are coupled. So this is kind of like called a couple system. So it's kind of difficult to solve a couple system, and you will see how we can use diagonalization process to decouple the system. All right, so like, you know, a couple, right? All right, a couple and decouple, right? So decouple, right? So 6 feet apart, for example. So I think you know what it means by a couple system. Couple is actually not spelled this way, but you know what I mean. And then a decouple system. So differential equations, you will see it in many different places in science and technology. In fact, the whole universe, one might say that the language of the universe is actually in differential equations, because all the things that we use to describe the universe is actually written in differential equation. For example, f equal to ma is actually a differential equation, because a is the second derivative of the distance functions. So this is actually also a differential equation. So we're going to look at how to solve this kind of differential equations, okay? Okay, let's look at another example right here. So we have a system of differential equation involving three variables, x1, x2, and x3. So these are the things that we want to find. So these are the functions that we are interested in, okay? So we want to figure out what is x1, x2, and x3. But unfortunately, just like in the previous system, most of the time, sometimes we cannot really write down the equations directly involved with this three quantity. Instead, we can write down a system of equation involving the rates. So we know the rates of x1, the rates of x2, and the rate of x3. And this is a coupled system in the sense that in order to in the rates equation for x1 actually also involve x2 and x3. The rate equation for x2 actually involve x1 and x3, so on and so forth. Okay, so we're going to use diagonalizations to decouple the system. Okay, and you'll see in a minute what is the meaning of decoupling the system, and it will significantly simplify our computations. Okay, so since this is a linear algebra class, it's no surprise that in order to solve this kind of equations, we are going to put them in a matrix system. Okay, so this particular system of differential equations can be written as this system. Okay, so putting into, basically we're going to encode it into a matrix system. So just FYI, especially for those who have taken Calc 3 before, you should know that if you have vectors x1t, okay, x2t, and x3t, so how do you take the derivative of this vector? Well, you take the derivative of this vector by taking the derivative component-wise, which means you take the first component, you take the derivative, you go to the second component, you take a derivative, you go to the third component, you take a derivative. So this is why if you let x, okay, as this vectors right here, then x prime is actually a vector where every component will be taking one derivative. So it will be derivative, derivative, derivative. So if you write x, okay, to be x1, x2, and x3, a 3x1 column vectors containing the function x1, x2, and x3. So this part here, it simply means dx1 dt, dx2 dt, dx3 dt. And this part right here, obviously, if you multiply it out, you will get this. Okay, so we successfully encode the system of differential equations into its matrix form. And for simplicity, we are going to write the system of equations, okay, as x prime equals to ax, where a is this coefficient matrix. Okay, so in order to solve this system of differential equations, the first thing you need to do is obviously you have to put it into a matrix form. Now, once we have this, we are going to concentrate on our coefficient matrix, which is our coefficient matrix A, which is right here. All right, so this is our coefficient matrix A. And second things that we need to do is to compute the eigenvectors and eigenvalues for this matrix A. And we know how to do that. We are going to skip the detail here. You can find the determinant of A minus lambda I and set it equal to 0. And you solve for the lambda, and you will see that we have lambda equals to -1. Okay, and lambda equals to 2. For lambda equals to -1, we can find two linearly independent eigenvectors, which we call V1 and we also call V2. So these are the eigenvector corresponding to this eigenvalue, lambda equals to -1. And here, for lambda equals to 2, we have one independent eigenvectors, which is given as V3. So we know from diagonalization process, if we construct a matrix P by putting in the V1 right here, V2 right here, and V3 right here, since they are linearly independent, all these vectors here are linearly independent. Remember that the concept of geometric multiplicity and algebraic multiplicity. So lambda equals to -1 have algebraic multiplicity 2, but also geometric multiplicity 2. So these are independent vectors, and this is going to be linearly independent with V3. So if you put your V1, V2, V3 as your column vectors into your matrix P, we know that this matrix P is invertible. And not only that, from the process of diagonalizations, we know that P inverse AP will give you this diagonal matrix, where this entries here is the eigenvalue for this eigenvectors. This entries here is the eigenvalue for these eigenvectors, and this entries here is going to be the eigenvalue for these eigenvectors. You can't. There's no one says that you have to put V1, V2, V3 in this order. You can also put V3 here, V2 here, v1 here. You also get a diagonal matrix, but the diagonal matrix will have entries like this. So you have 2, and then you have -1, -1 instead. So that's not going to be a problem as long as I just need a diagonal matrix, okay? So that's not going to be a big problem if the diagonal matrix looks different, okay? So suppose, let's follow the notes and says that our P is constructed this way. So we will have P inverse AP equals to D. Now here comes the critical steps. So here comes the key steps, okay, which in the notes is refers to step 3, change of variable. So we are going to introduce variable y1t, variable y2t, and variable y3t. And we are going to put all of them into a column vectors, and this is what we're going to call the column vectors y. And how do we construct this y1, y2, and y3? We construct it in such a way, okay? We didn't construct it, we give it a very mysterious way to represent this y. So we don't really write down what y is, what this column vector y is immediately. Instead, we are going to write this y as this. So the key step here is to do this change of variable. I'm going to write my y, okay, like this, okay? So I'm going to write my y like this. So I'm going to write my y satisfying this particular equations right here. I mean, if you want to, you can also write your y is P inverse X like that, but at the moment, I don't want to involve P inverse, so I'm just going to write y, the vectors y, like this. So you can also kind of see that the y, obviously, the vector y obviously has some relationship with the vector x. Okay, this is, and the exact relationship is given by these equations. Okay, so for example, this is what happened here. So for example, x and y are related this way, okay? Now, okay, so just very importantly, I just want to point out that this matrix P here has no variable T whatsoever. This matrix P here is a matrix containing all these fixed numbers. So they are not function of time, okay? The matrix P is not a function of time. And I claim that if you take the derivative of this vector x, this is the same as taking P, the matrix P, multiply the derivative for this column vector y. And the reason is straightforward. If you can see that, you can also refer to the notes. And from the notes right here, okay, you can see why this is the case, okay? So I'm basically write down all my x and y, okay, right here. And then I'm taking the derivative, okay? And you will see that after you take the derivative, we actually do have this relationship x prime is equals to py prime. So it's not a big mystery. If you write x is equals to py, you kind of do a change of variable, then the derivative x prime is really equals to py prime. So why do we do this? So we do this for one purpose and one purpose only. So we're using this diagonalization process. You'll see that why diagonalization process will come in. We want to decouple the system, okay? We want to decouple the system so that systems will involve equations that's easier to solve. So now, so we are right here. Okay, so once that we have x equals to py, okay, so we're going to substitute that, and x prime equals to py prime. So we're going to substitute that into this equation, x prime is equals to ax, right? So x prime right here is now our py prime, okay, and then a, and then our x here is py, okay? And multiply the inverse to the other side. So you have y, this column vector y prime is equals to P inverse AP y. Now P inverse AP is our diagonal matrix D. So what happened is once you have performed the change of variable, you will see that your y prime here is actually dy. So this is key. So your y prime here is actually dy. So what is y prime? Y prime is a column vectors involving the derivative of y. So you have y1 prime, y2 prime, y3 prime. Okay, so this is our y prime. So y prime is equal to diagonal matrix here, multiply y. So do you see that? This is key. So this is what we call a decoupled system. Why do we call this a decoupled system? Because with this equation, it's basically tell you that y1 prime is equal to -1 times y1t. So your y1 prime only involve y1. Your y1 prime the rate for y1 does not involve some other quantities like y2 and y3. They are completely decoupled, all right? So your y1 primes is equal to -1 minus y1's t, and if you look at this system right here, your y2 prime is going to be negative y1 y2. So this is again a differential equations involving the functions y2 only, and this right here y3 primes is going to be 2y3. So this has happened. You get this equation from this matrix multiplication. You multiply out this matrix and you will see that y1, the derivative functions, the derivative equations for y1 only involve y1. The equation involving the derivative for y2 is only involving y2, and the derivative for the equation that involving the derivative of y3 is only involve y3. And these are what we call Kitt's differential equation. These are the things that you know how to solve. This is separable differential equations, so they can be solved very easily. For example, dy1 dt is equals to negative y1t. So these are separable differential equations. This is basically nothing but this, and you integrate, you have log y1 equal to minus t plus a constant. So this will give you y1. Okay, so this will give you y1 equals to some sort of a constant. I call it c1 and e negative t. So this is your y1. All right, so this is your y1 right here. So right here, you can see that if you solve it, I'm going to write this like k1, right? So I write like k1. So these are very easy separable differential equations. Do the same thing for y2. You get that also. And if you continue to do that, you will see that at the end, you also have y3 that is going to be written like this. So these are completely decoupled system, and because they are decoupled, they are easier to solve. So now we have our y. So we have this. What is our yt? Our yt is our y1, y2, and y3, and we have that. Okay, we know exactly what is y1, y2, and y3. And so the last step is just going to make a connections back to the original equations, original functions that we are interested in, which is our x1t, x2t, and x3t. So this is the same as all type of change of variable problems. You change it to another variable, solve it, and you have to change it back. So changing it back, okay, you will have to, this is what I call step 5, you have to reintroduce their relationship. So these are their relationships. So x here is related to y exactly like this. So you write it out, that's your x, this is your vector p, the matrix p, and this is your y. And instead of multiplying out using the traditional multiplication like this and this and so on and so forth, you can use that particular view, that matrix multiplications like this can be viewed as a linear combination of the column vectors. So basically you have this multiply this column plus this multiply this column plus this multiply this column. So you have expressions that looks like this. We wanted to write like that because now, as you can see, if we write like that, you can see our solution x here is nothing but a constant. Okay, multiply the eigenvectors v1 and then multiply the number. This is a scalar, this is an r. Okay, e negative t is real value functions. So you have a scalar, you have a vector. This vector is your eigenvectors, corresponds to this eigenvalue right here. You see there's an eigenvalue right here. All right, and then plus a scalar, okay, another vectors. This is our v2. Okay, so here this is again our eigenvalue corresponds to this particular eigenvectors, and we also have this one right here, a scalar, a scalar k3. Multiply another vectors. This is the eigenvectors v3, and here you have the eigenvalue corresponding to these eigenvectors. So we can write down our solutions like this. So we managed to solve that system of differential equations. Okay, we managed to solve that system of differential equations, and we know the solution looks like this. Okay, and we know the solution looks like this. And the reason why we managed to solve that differential equation is because we managed to decouple the system. We managed to decouple the system, solve the decoupled system, and then put it back. All right, so that's the strategy, and you can clearly see how the diagonalization process helped us in achieving this goal. right? Why can we decouple the system? We can decouple the system precisely because your system here is involving this diagonal matrix right here. So this is where the diagonalization process help us in solving that differential equation. Okay, so let me say that one more time. The reason why the thing can be decoupled is because we have a diagonal matrix right here. Okay, so this is how we use the diagonalization process to solve a system of differential equations. All right, so now we're going to look at how to apply diagonalization process to solve another type of problem, which is known as the difference equations, also known as the recursive equations. And these are the equations that looks like this. So you've been given x0 is 0, and you also be given that x1 equals to 4. And with that, we can figure out what is x2. So x2 here, according to this equation, you have to take t equals to 1. And that will give you 6x1 and then minus 5x0. And since we have x0 equal to 0, so this whole thing is 0. And this is 6 times 4, so it gives you 24. So if you want to compute x3, no problem. We can again look at these equations, and you can see it will involve x2. And it will also involve the value of x1. So it always involves the values 1 step before and 2 steps before. So, I mean, it's okay. We can solve equation. We can get our equations. We can get all our x values out like this, but it's very inconvenient. So instead, I will want to write down my solution as xt equals to something, and that something is involving t only and does not involve t minus 1 or t minus 2. So those are known as the closed form solutions. So how do we get the closed form solutions? Well, since this is linear algebra, the first step is going to put the equations into a matrix form. And this is going to be a little bit strange if you haven't seen something like this before, because we only have one equations. How are we going to put it into a matrix form of size, let's say, is 2 by 2? So what we're going to do is that we're going to recreate this xt plus 1. So xt plus 1, as you can see right here, okay, xt plus 1, as you can see right here, is 6 of xt minus 5 of xt minus 1. So the first row is okay. So the first row, okay, is doing this. So xt plus 1, okay, is 6xt minus 5xt minus 1. So we managed to encode that system in. But in order to create a 2 by 2 matrix right here, we're going to have to write down redundant equations. So the redundant equation is, in order to match up with this one here, xt. So I'm going to write xt as 1xt and then 0 of xt minus 1. So the second equation right here is a tautology, right, so to speak. It's something that is obviously true. We are basically writing down xt equals to xt, right? So in the second row right here, that's what we do. The reason why we do that is to create this matrix of size 2 by 2 right here. So that's the reason why we're doing that. The key things is that we wanted to have the first equation. The first equation is the key parts that we need to have, and that is given right here. So we encode the equation right here, but in order to have a 2 by 2 matrix, we write down something that is a little bit redundant, which is xt equal to xt in our second row. Okay. Now, I'm going to change my variable a little bit. I'm going to write this as ut plus 1. So ut plus 1 is a column vector, which stands for the xt plus 1 and xt, right? If you do that, then our ut is going to be xt, right? And then xt minus 1, right? So this is t plus 1, so this matches with that. So if I do t, this have to matches with this. And this one here is one term less than this. So if this is t, this has to be t minus 1. So the entire equation right here, the equation star right here, by using this terminology right here, you will see that the entire equation star can now be written as equations like this. So these are column vectors, right? ut plus 1 equals to a times ut. And we can also encode this initial condition here. So we've been told that x0 is x1 and x1 is 4. So that actually will give us our vector u1. So again, if you put u1 inside here, that is going to be our x1 and x0. And we know that x1 is 4. Our x1 is 4 right here. Our x1 is 4, and there's a typo right here. Our x0 is actually 0. Okay, so we have that. So now we have a system ut plus 1 equals to aut, and we also have u1 equals to 4, 0. All right, so now we have a 2 by 2 matrix A. Let's diagonalize this matrix, okay? This matrix, if it's diagonalizable, then let's diagonalize it. And computing the eigenvalues, we got lambda equal to 5, lambda equal to 1, and we can choose 5, 1 as its corresponding eigenvectors for lambda equal to 5, and we can choose 1, 1 as the corresponding eigenvectors for lambda equal to 1. So we are doing even though the context is different this time from the previous example, but we're doing diagonalization process. So diagonalization process for a square matrix is the same, right? So you select your matrix P, okay, you put in your vector 1, 1 right here, you put in another eigenvectors 5, 1 right here, then you would know P inverse AP will equals to D, and that D here, this 1 here is the eigenvalue corresponding to this eigenvector 1, 1. Right, and this eigenvalue 5 is the eigenvalue corresponding to this eigenvectors 5, 1. So this is diagonalization process, nothing very fancy. So it's just diagonalization process. So once we have that, okay, once we have that, we are going to resubstitute. So we originally have A, right, in the matrix here. So we are going to take this and rewrite, okay, so P inverse AP is equal to D. So what is A? I'm going to have A now as PDP inverse. So A is PDP inverse. You're going to substitute it into here. That's the reason why you see that we have PDP inverse. So now my equations here is going to be like this. Okay, so now my equation here is going to be ut plus 1 is equals to PD, right? P inverse, okay, ut. All right, so let's do some enumerations, okay? So t equals to 1, you have u2. u2 is PDP inverse u1, okay? ut equal to 2, so you have u3. So u3 is PDP inverse u2, but we have u2 from the previous step. So you substitute here, and now you can see this is the key part right here. So u3 is PDP inverse, right? And u2 is PDP inverse u1, and this is the key part right here. The P inverse and P cancel out, right? The P inverse and P cancel out. And D multiply together by definition, that's D square. And we know how to compute D square easily, because if your matrix is diagonal, D square is just nothing but the diagonal entries here, raise it to 2. So this is like D1 square, D2 square is 0, 0. That's the reason why diagonalization process is important, because in general, if you raise the power of a matrix, you don't really know how it looks like. But if you raise the power of a diagonal matrix, well, they all looks pretty easy. They all looks like that. So now, after you do all these enumerations, you will see that U2 is going to give you this. U3 is going to give you this. Okay, U4 is going to give you this. Okay, starting to see a pattern now. So the pattern is, okay, if this is 3, this is power 2. If this is 4, this is power 3. It's always P and then D something and then P inverse and then U1. So in general, if this is T, then this will be T minus 1. And then now we'll have UT is equals to PD to the power of T minus 1 P, okay, U1. So that's our equation right here. That's our equation right here. And we are going to compute this, okay? So if you follow right here in the notes, this is our step 4. Let's say, okay, for simplicity of computation. So let's say for simplicity of computations, just, I mean, it's nothing much, okay, just for simplicity of computations. All right, for simplicity of computation, I'm going to call this vector C1, C2. That's what I'm saying. P inverse is a 2 by 2 matrix. Okay, U1 is a 2 by 1 vectors. So this is nothing but a 2 by 1 column vectors. So whatever that thing is, I'm going to call it C1, C2. All right, so it's for simplicity of computations. You're going to see why in a minute. It's very easy. Okay, so if you do that, this equation UT right here, this equation UT right here is nothing but P, right? And then you have your eigenvalue here, raised to the power of T minus 1. Second eigenvalue here, raised to the power of T minus 1. And this is C1, C2, okay? And this matrix P here is nothing but V1, I'll call eigenvectors, v2. And if you multiply this part right here, you will get v1, v2, and you will get a column vector that's lambda 1, t minus 1, c1, lambda 2, t minus 1, c2. And again, when you multiply matrices like that, you can use the perspective of this matrix multiplication can be written as a linear combination of the column vectors. So you take this, multiply this column vector, plus this, multiply this column vectors, and that's what happened if you multiply these two matrices together, okay? So take a look right here. Right here, this term here is just a number, okay? So you have a number, okay, another number. So let's say if I have like v1, right? v2 I've multiplied 2, 3. So what is that? That is 2 of this vector plus 3 of this vector. So it's the same thing right here, okay? So exactly the same thing right here. You are going to have this, multiply this vector, this, multiply this vector, and it's going to be in this form. So this is a perspective that we take a long time ago when we first learned how to multiply matrices. This is writing a matrix multiplications as a linear combinations of the column vectors. So based on this, you will get to see that our ut is going to be like this, okay? Because that is our lambda 1, and that's the v1. This is our lambda 2, that's our v2. So actually this is just 1 raised to any power is still 1. So now our equation is just basically like that, okay? Pretty easy. We can even ignore this. This is just 1. And the only last thing to figure it out is what is the exact value of c1, c2. So what is the exact value of c1, c2? We know the matrix P. Matrix P is not something mysterious. We actually know the matrix P. So we can find the inverse and multiply it with the u1, which is for 0. And it turns out that our c1 is actually -1 and c2 is 1. So now finally, we are going to have an equation ut that involves only t. Okay, so if you write everything's out right here, this is our ut. And right here, if you combine back, you will get this. And now we have two equations, okay, because these two column vectors are equal to each other if and only if the columns, the corresponding component here are the same. So now you actually, I mean, I don't, the second one is redundant. If you have the first one, you also have the second one, obviously. So you have this as our formulas. Okay, and the t here start from 0, 1, 2, and so on and so forth, right? Okay, or you have this one right here. This is redundant because if you have the first one, you obviously also have the second one. So we don't really need this. You just take a look at this. This is our closed form formula. Okay, this is our closed form solutions. Our xt now no longer depends on the previous steps, and definitely does not depends on the previous steps. And we have that. Okay, that is our closed form solutions. And you can see if you write it out, so you have x0 equal to 0 when t is equals to 0, all right, and t is equals to 1, that gives us the 4, that's our initial conditions. And when t equals to 2, okay, you have 24, and then you have 124, so on and so forth. So the recursive relations is no longer recursive because we found a closed form solutions. And why does this work? Why does this work, right? Why this method works? Well, it's because of diagonalization process. Exactly where we use the property of diagonalization process. We use it exactly here. If this matrix is not a diagonal matrix, this part here is going to be supermassive, okay? If you have a matrix which is not diagonal, and if you raise it to a certain power, you can see what's the other pattern, okay, of that particular matrix. But if your matrix is diagonal and you raise it to a certain power, well, that is nothing. The power of that matrix is nothing but this. Okay, and that is precisely where the diagonalization process is used. Okay, all right. Okay, so this concludes our discussions on eigenvectors and eigenvalues, and also the process of diagonalizations and applications of diagonalizations. So we come to the end of the, almost at the end of the semester, and the last topics, the last major topics that we're going to talk about is some geometry that is in our end, leading to the least square method. All right, so we are going to move in that direction now, and so I will hope you enjoy the last part of the course. All right, I'll see you in the next video.